Hi, well, good afternoon, and thank you so much for inviting me here today to speak. My name is Joseph Bard. I'm a geographer with the US Geological Survey Cascades Volcano Observatory in Vancouver, Washington. So a really important element of my work as a geographer is making maps, and so it's a real privilege to be able to have the chance to come here today and talk to you about the volcano hazard maps, the past, present, and the future of volcano hazard maps. Before I really get into the talk, I do want to say that in this talk, I will show 3 images of cities that were devastated by eruptions. And while I will not be showing any images of any injured people, I just wanted to let you know that in this talk, I will speak about some very tragic events in which many people did lose their lives. So just be aware of that, please. So throughout most of human existence, we really haven't known anything about how volcanoes work. And because of their immense power, they have terrified us, they have fascinated us, and they really remain places of great spiritual importance for many people all around the world. And this lack of knowledge about volcanoes has sometimes resulted in really tragic and deadly disasters. For example, possibly the most famous volcano disaster in history, the eruption of Mount Vesuvius in 79 AD that destroyed the Roman city of Pompeii near modern-day Naples, Italy. So before the eruption of Vesuvius, it had literally been quiet for hundreds of years, and the volcano was just considered extinct. The volcano was covered with vegetation, and so the eruption was completely unexpected. But within moments after the eruption, the city was so completely covered by hot volcanic ash that the ruins were not uncovered for another 1,700 years. It's only really in the last approximately 100 years or so, with the emergence of the science of volcanology, have we really begun to understand how volcanoes work. And as the science has evolved, so has our ability to map and analyze volcano hazards and their impacts. So volcano hazard maps are a really super important tool for us for communicating about volcanic hazards and for mitigating disasters. In the US, there are 161 active volcanoes. And this includes the territories and some US territories, including the Commonwealth of the Northern Mariana Islands in the Western Pacific and American Samoa in the South Pacific. We consider a volcano to be active if it has erupted since the end of the last ice age, which is around 12 to 15,000 years ago, depending on where you are. Or volcano monitoring equipment positioned on the volcanoes can actually detect signs of an active magmatic system in the volcano. So 55 of these volcanoes in the United States are considered very high threat or high threat. And this is based on the potential for an eruption to impact people or important societal systems. Today, the USGS Volcano Hazards Program operates 5 volcano observatories. There's the Hawaiian Volcano Observatory in Hilo. There's the Alaska Volcano Observatory in Anchorage and in Fairbanks. There's the California Volcano Observatory down in the Bay Area. There's the Yellowstone Volcano Observatory, and as well as the Cascades Volcano Observatory in Vancouver, Washington, where I work. So the mission of the USGS Volcano Hazards Program is to enhance public safety and minimize social and economic disruption from volcanoes through the delivery of effective forecasts, warnings, and information about volcano hazards based on a scientific understanding of volcanic processes. At the CVO where I work, it was formally established in 1982. This is 2 years exactly after the eruption, the famous eruption of Mount St. Helens in 1980. It was recognized that with all the active volcanoes that there are in the Cascades, it was a really good idea to have a permanent volcano observatory facility in the Pacific Northwest. And at the Cascades Volcano Observatory, or CVO, there's really 4 strategic elements that guide our work. The first is volcano monitoring, then there's volcano hazard assessments, there's research on active volcanism, and then last piece is really hazard communication with the public and with authorities. So the CVO is responsible for monitoring the volcanoes in Washington and in Oregon, and as well as Idaho. We conduct research on many aspects of active volcanism and respond to volcanic disasters locally as well as abroad. And a very important aspect of our work is providing information to other government agencies, to land use planners, to emergency responders, the news media, to schools, and to the general public. So, and map products are really an important tool for communicating about where these areas are that might be impacted by eruptions and what could happen during an eruption. Let's take a look at some of these volcano hazards. Let's first start with a mental imagery sort of word association exercise. So hold in your mind the very first image that pops into your head when you see this phrase volcano hazard. What does that look like? Does it look possibly like this, lava erupting out of Kilauea volcano? Or perhaps like this, a big pyroclastic flow running down the side of Mount Pinatubo in 1991 in the Philippines? Or for Washington locals, maybe something a little more like this, where you have a big ash cloud blotting out the sky after the eruption of Mount St. Helens in 1980. Volcanic eruptions are very complex, and the hazards that are associated with volcanoes can take many forms. For example, in this map, which is a simplified hazard map of Mount Rainier, which we'll see again in the future, this area I'm highlighting here with the arrow is the near vent hazard zone. And the vent of a volcano is the source of an eruption, the place where rock particles, where ash, where gas, where lava all come out of the ground. Lava flows are one type of near vent hazard. This image is of a lava flow of Kilauea volcano in 2018. Now, most Cascades volcanoes do not produce very fluid lava, just like we're seeing here. However, there are exceptions. And one exception is the Newberry volcano, which is just south of Bend, Oregon. So most lava flows in the Cascades are unlikely to reach communities because not a lot of people live right up and close to the volcanoes. However, the heat from the volcanoes could definitely start forest fires in these forested volcanoes. Pyroclastic flows are another near vent hazard. Pyroclastic flows are super hot, super fast flowing torrents of hot rock and ash and gas. And it's another great near vent hazard is ballistic blocks. Explosions of the volcano can hurl rocks we call ballistic blocks at speeds of 500 miles an hour. So even the small rock traveling at that speed could definitely kill or injure somebody. So the thing really to know about near vent hazards, including pyroclastic flows, lava flows, and ballistic projectiles, is that they will burn, bury, or crush almost anything that they encounter. So luckily though, the formula to be safe from near vent hazards is quite simple. Just stay away from the volcano if it is erupting or if it's in a period of unrest. Along these river valleys that the arrows are pointing to, these are Lahar hazard zones. Now, Lahars are fast-flowing slurries of mud, water, rocks, and debris that can travel down the slopes of volcano, travel down river valleys, excuse me, that begin on the slopes of volcanoes. Lahars are a very important hazard to be aware of in the Cascades. Large lahars can travel many tens of miles away from the volcano and infect communities very far downstream. Now, lahars can occur in several ways. For example, on ice and snow covered volcanoes like we have here in the Cascades, during an eruption, the hot rocks and gas coming out of the volcano can melt the ice and just create a massive deluge of water that sweeps down the volcano and sweeps up rocks and debris and whatever else is in its path. Lahars can also be caused by massive scale slope failures on the side of a volcano. It's sort of almost a landslide of sorts that essentially liquefies as it starts to break up and run down the volcano. Lahars can destroy or bury almost anything in their path as well. Their impacts often last much long after the eruption is over. The sediment that's deposited in rivers can increase the bed height and increase flooding. The sediment can also impact water quality and fish habitat for years to decades after an eruption. In this image, you can see the mud line that's left on the trees after a lahar swept through this area from the May 18th, 1980 eruption. And the person, it's circled on the riverbank for scale, just to give you a sense of just how high this lahar was as it swept through this area. So lahars pose the biggest threat to people here in the Cascades, and Rainier is definitely the most concerning volcano. And this is because many people live alongside the rivers where lahars have flowed in the past and definitely could flow again in the future. Now, to be safe from a lahar large enough to reach densely populated areas is really the essential strategy for a life-saving strategy is just evacuation in the event of a lahar, evacuating from valley floors to higher ground. So volcanic ash and tephra are another hazard. Volcanic ash and tephra are particles of rock, or volcanic rock that are produced during explosive eruptions. When eruption occurs, areas downwind the volcano are affected by ash hazards. Now, large particles of ash and tephra will fall within a few miles of the volcano. Or really fine particles can get suspended in the atmosphere and travel hundreds to even thousands of miles downwind. Now, larger eruptions produce more ash, and the stronger winds will carry ash further downwind. Ash can be very irritating to the eyes and sinuses of people and animals. It can make it really difficult for animals to forage and find drinking water. Ash reduces visibility, and it's incredibly abrasive. It's just little chunks of rock, so it can really easily damage machinery, and aircraft in flight are especially susceptible. Electrical grids and water supplies are also vulnerable to ash fall. If ash is falling, the best plan is to shelter in place indoors and try to keep ash outside and try to minimize driving as much as possible. So we don't really show ash in this map, and that's because basically anywhere on this map could be affected by ash from an eruption, depending on the size of the eruption and the direction the wind is blowing. And also not just from this volcano, but from other volcanoes nearby. So while this is not a complete list of volcano hazards, these are the volcano hazards that are most often the subject of hazard maps. So speaking of maps, let's move on to talking about volcano hazard maps of the past and how Science of volcanology and the invention of hazard maps has revealed unknown volcano hazards. And I really want to thank my colleague John Ewart for sharing a bunch of the work that he put together on this subject with me to allow me to borrow this to put it in my presentation. So thanks so much, John. So today, a Google search will turn up of volcanic hazard maps will turn up dozens of maps, but volcano hazard maps have not always been so ubiquitous. In the early 20th century, volcanology began to emerge as a modern science, and in volcanology, really big disasters propelling the science forward in big leaps. One example of one of these terrible disasters is what happened in 1902, the eruption of Mont Pelée on the island of Martinique in the French West Indies. As USGS scientist Rick Hoblet wrote, a ground-hugging cloud of incandescent lava particles suspended by a searing turbulent gases moved at hurricane speed down the southwest flank of the volcano, reaching St. Pierre at 8:02 a.m. Escape from the city was virtually impossible. And almost everyone within the city proper, about 26,000 people, were killed. You're seeing a before and after photo here. So this phenomenon that destroyed St. Pierre was a pyroclastic flow. And in 1902, this was completely unknown to science. But since then, it has definitely been witnessed at many other volcanoes around the world, including Mount St. Helens in 1980. So in the early years, the emerging science of volcanology was really devoted to accurately predicting eruptions and developing mitigation strategies. This is a map from 1930, and it's of Merapi volcano in Indonesia. It's one of the earliest volcano hazard maps we see. In 1919, 5,000 people were killed by an eruption of a volcano called Kelut, which really motivated the Indonesian government to produce the first hazard maps for frequently active volcanoes. Hazard zones on this and other similar maps in this series showed the topography of the volcano and also areas that had been impacted during recently observed observations. And this is kind of an important aspect of these maps. These first early maps really only show what has happened in the recent past based on firsthand observation. So hazard maps that begin to forecast potentially impacted areas don't even really emerge until the 1960s. This is a map of Soufriere de Guadeloupe volcano on the island of Basse-Terre in the French West Indies, not far from Martinique, where Mount Pelée, the disaster that destroyed the city of St. Pierre on Martinique. And so what this map shows is the areas of the island that are susceptible to pyroclastic flows if the volcano on this island erupted and it was similar to the eruption of Mount Pelée in 1902. This is really significant because it offers a forecast based on the premise of a specific event occurring in the future. And so it's a scenario-based map or conditional hazard map. And it really explores this, if this, then that type scenario. In 1959, the United Nations asked the International Association of Volcanology to determine the parameters that were really appropriate for volcano monitoring and for protection of lives and property threatened by eruptions. One real key recommendation was that the science of volcanology and volcano observatory should work towards making eruption forecasting reliable, and the notification and notifying governments and regions regarded as dangerous that are in the neighborhood of volcanoes, having considered all the various possibilities. And really what they're doing here is implying the need to produce really comprehensive volcano hazard maps. So these maps from 1964 show the Auckland volcanic field in New Zealand, and they're significant because they pioneer a use of a relatively new scientific technique at this point, which was radiocarbon dating. And this was used to complement traditional field geology to establish a chronology and to allow for the estimation of quantitative probabilities of future eruptions in this area. So let's turn back to the United States now, because at this time, the same time in the 60s, there was some really revolutionary work taking place in Washington that would change the course of volcanology and volcano hazard maps forever. So the story starts in this area right here, just a little bit to the northwest of Mount Rainier. So at this time, large volcanoes like Mount Rainier were kind of viewed by science to be essentially relics of the past and no longer active. Ooh, foreshadowing there for you. So let me introduce you now to Dwight Rocky Crandall. In 1953, he was a USGS geologist in the Engineering Geology Division based in Denver. And he was assigned to make a geologic map of the area near Lake Tapps in Washington. Now, he was not there for the purpose of looking at volcanoes specifically, but and this is on the left, you're seeing the completed geologic map that he was there to make, that was published in 1963. But in his field investigations, Crandall was re-examining a layer of earth that was a combination of sand and silt and rocks that ranged from small pebbles to boulders that are 8 feet in diameter. And these are the salmon-colored areas of the map where the arrows are pointing to right here. So this area had first been mapped in 1899, and the salmon-colored places on the map that I'm showing right now were reckoned actually to be related to the glaciers of the last ice age. And this was definitely a reasonable interpretation for the time, given that the Puget Sound area and the surrounding lowlands are really, really dominated by post-glacial landforms. But Crandall saw two things that did not fit with the glacial explanation. The first was that there was wood particles, including things like whole logs, mixed in with all these rocks. This is curious because trees do not grow on glaciers, and so there wasn't really, it's hard to imagine how the trees could have got in there. The second piece, though, was that the deposit contained clay-sized particles. Now, clay is actually a geologic size classification for particles that are very, very, very small. In fact, they have to be less than 0.002 millimeters to be considered clay. Now, clay particles are only created when rocks are dissolved by chemicals, like hot acidic fluids. And they're definitely too small to be created by the forces of friction, even in massive glaciers like the size of those at the end of the last ice age. So Crandall followed this deposit that he found all the way upriver, all the way up to Steamboat Prow near Camp Sherman on Mount Rainier. So Mount Rainier, like many active volcanoes, has an active hydrothermal system. And there's acidic superheated fluids within this hydrothermal system that are slowly weakening the rocks from within. And they create the conditions for large sections of the volcano to really break apart and fail and become lahars. What Crandall realized is that the deposit he was found was actually a massive lahar. He renamed it the Osceola Mudflow, and is the largest such lahar that has ever been discovered. Today, the Osceola Mudflow can be found extending 20 miles away from the volcano and spread across an area that is in some places up to 10 miles wide. In some places, the deposit is 350 feet thick. So this discovery proved that Rainier was, and still definitely is today, very much an active volcano, definitely not a relic of the past, as was sort of the popular scientific opinion of the day. So I've said the word lahar a number of times, but before I go any further, I want to pause to show you a short video of a lahar to give you a sense of what they look like, and then we'll return to our story. So this is a very small lahar at Semeru volcano in Indonesia. It's many, many, many times smaller than the lahars that would threaten populations around Mount Rainier. But I still think this video is useful for demonstrating just how powerful these events can be, even really small ones. So keep an eye out for some, at the end, there's some, this flow just moves some pretty sizable boulders, and then after that, we'll get back to our story. So Crandall's discovery of the Osceola mudflow led to further investigations around Mount Rainier. And so I wanted to introduce you to another key figure in this story as part of those investigations, and that's a USGS geologist named Don Molyneux. Don Molyneux actually, incidentally, was a Washington local. He grew up in Camas, just east of Vancouver, Washington, and did his PhD work at UW. So Crandall and Molyneux first met in 1953, and their collaborations in the 60s and 70s, mapping the Cascades volcanoes, would define the future of volcano hazard assessments and volcano hazard maps. For example, in 1967, Crandall and Molyneux authored the very first USGS volcano hazards assessment entitled Volcano Hazards at Mount Rainier, Washington. And one of the significant findings was that there was evidence that Rainier had actually produced many large lahars in the past, including the Osceola mudflow found in this kind of dotted area, and another one called the Electron mudflow, which is the most recent large lahar that came down the Puyallup Valley. However, this report does not have a map. It only features this small graphic that was an inset on one of the pages of the report. So today we know that Rainier has produced a lahar large enough to reach currently populated areas about once every 500 to 1,000 years. 6 years later, Crandall and Molyneux made the first volcano hazards map of Mount Rainier, and really the world's first modern volcano hazard map. It shows all of the areas that could be affected by potential eruptions, and thus it is an unconditional hazard map. This results from very, very detailed geologic work and analysis, really the entire range of the past eruptive behavior of the volcano. Today, nearly all volcano hazard maps in the world endeavor to follow this approach. So during that investigation, Crandall and Molyneux kept finding ash layers from another volcano between the layers of ash from Rainier. Does anyone have any guesses of what volcano this might be? Well, if you guessed Mount St. Helens, you get 100% on the mid-talk quiz, and great job, gold star. So with the benefit of hindsight, we definitely know why. This graphic shows the eruptions in the Cascades for each volcano over the past 4,000 years based on the geologic record. It's pretty clear that Mount St. Helens is definitely the most active volcano in the Cascades. So Crandall and Molyneux's really rigorous geologic fieldwork led to another publication in 1978 called Potential Hazards from Future Eruptions of Mount St. Helens Volcano, Washington. Now, this is the first example of a totally modern volcano hazard assessment as a report, as well as the hazard map. There's really one line, though, that towards the end of this paper, which really stands out, and that's that, and it reads, Mount St. Helens behavior pattern suggests that the current quiet interval will not last as long as 1,000 years. Instead, an eruption is more likely to occur in the next 100 years, and perhaps even before the end of the century. Well, as it turns out, Crandall and Molyneux knew what they were talking about, because 2 years later, it was the famous eruption of Mount St. Helens in 1980. However, in the lead up, the hazards map that Crandall and Molyneux had created was an absolutely essential tool for communicating about the hazards, about that eruption. And really today, volcano hazard maps such as these continue to be the foundation of preparedness efforts, for prioritizing volcano monitoring, and for responding to volcanic unrest and eruptions around the world. So to really summarize these stories of Crandall and Molyneux's work, their work on volcano hazards rose organically while they were just making the standard US geological superficial geology maps. Initially, they received a lot of pushback from the community about their findings about the volcanoes, but their homework was the proof. And eventually, with the weight of their evidence, they're able to convince people. And my colleague John Ewart says, evidence is evidence, and that's how science works. So I love that. So I want to close this section with a final thought about the science of volcanology and how it came from this idea of showing simple maps of firsthand observations of recent events to being really essential tools for holistic understanding of the complete hazard landscape at a volcano. Our foundational premise of the science of geology is this idea of this principle of uniformitarianism, which is the assumption that the same natural laws and processes that operate in our present-day scientific observations have always operated in the universe in the past. Therefore, by studying the present, it is the key that unlocks the past. So the genius, though, of Crandall and Molyneux's work is that they actually inverted this premise and proved that by studying the evidence of past eruptions, that they can reveal what is most likely to occur again in the future. And in so doing, they created basically the central tenet of modern volcanology, and that is the past is the key to the future. That takes us to hazard maps of the present. The hazard maps, in the present, the hazard maps are propelled forward by really 2 major eruptions and also the age of the computer. And this is a building on the pioneering work of Crandall and Molyneux. So let's start with the eruptions first. The first is the 1980 eruption of Mount St. Helens. Absolutely one of the most important eruptions in the history of volcanology. Returning to a line I mentioned earlier, that volcanology takes really large steps forward in big eruptions. Well, the place where Mount St. Helens erupted, and also the moment in time in which it erupted are huge factors for this. And the U.S. is a prosperous country. Mount St. Helens is right near 2 major U.S. cities. The eruption occurred first thing in the morning in broad daylight on a clear day in May, which is not a given for sure in the Pacific Northwest. Also, the moment in technology when it happened, with sort of the advent of personal computers, this was a huge deal. And of course, the events that transpired at Mount St. Helens itself really would change our understanding of volcanoes forever. And so some of my colleagues have actually given some talks about Mount St. Helens that are part of this Whidbey Reads series, and they will be hosted on the Cascades Volcano Observatory website, including with this one too. So please check those out if you're interested in more detailed story about the Mount St. Helens eruption. So the second eruption occurred in Colombia in 1985. And this image shows the remains of the town of Armero that was devastated by a lahar. The town was essentially buried, and 25,000 people died after a relatively small eruption of a volcano called Nevado del Ruiz. So this was really significant here in the United States because Nevado del Ruiz and Mount Rainier share a lot of really important similarities. They're both really big, tall mountains with lots of ice and snow on top. There's large populations that live in the areas where lahars are known to have occurred. At Mount Rainier, this evidence of lahars is in the geologic record, but in Nevado del Ruiz, there have actually been 2 previous lahars in historic times. Yet, even though people had, and this disaster occurred, despite the fact that people actually had witnessed these lahars and actually even written about it. So the thing that's really exceptionally tragic about the Armero situation is that it was entirely preventable. The eruption was not a surprise. nor was the fact that it could produce a lahar. It was really caused entirely by just a failure to act. And so, a lot of the work that we do with USGS and the Volcano Hazards Program is really dedicated to making sure that tragedies such as another tragedy such as what happened at Armero never happen again here in the United States or abroad. So starting in the 1990s, creating hazard assessments and maps for all dangerous volcanoes in the United States really became a priority. And so I'm going to show you the dates in which the hazard assessments were completed for all the volcanoes in the Cascades. And so all these are really built on the same technique that was pioneered by Crandall and Molyneux. So these efforts, though, included an expansion of some techniques. This on the left here, we're seeing the inclusion of a probabilistic map of ash hazards here shown at a regional scale for the entire Cascades. Also on the right here, is forwarding this concept. This map begins to forward the concept of these low probability, high consequence events, sort of these maximum credible events or these really worst case scenarios. And so these are really important for informing land use plans and for emergency managers. They really like to plan for this type of worst case scenario. The imprint of modern computing is absolutely everywhere in our daily lives. And in hazard mapping, desktop computers and commercially available mapping software really have changed everything. Among the most impactful things on mapping the Earth has been the development of a data format called the Digital Elevation Model, or DEM. Well, what is a DEM, you might ask? Well, you're actually looking at one right now. And a way to think of a DEM is it's really just a photograph of the Earth's surface. But whereas a typical digital photograph stores information about color, the DEM actually stores elevation values for places on Earth, and they can be uploaded into mapping software and used to visualize the Earth. And so, you might have known that sort of jellyfish-shaped image is actually an aerial view of Mount St. Helens. So this DEM was produced using a technique called LiDAR, in which an instrument is mounted in a plane and flies over an area of interest and scans the ground with a laser. And we'll return to this idea in a little bit later. So while DEMs do a fantastic job of displaying terrain, they have many more uses beyond just visualization. So the Armero disaster really greatly motivated people in the volcano science community to better understand lahar hazards. And DEMs allowed USGS scientists to develop a computer program called Lahars, which estimates the areas that could be potentially impacted from a lahar, if a lahar of a certain size occurred at a given volcano, really anywhere in the world. This thing was a huge breakthrough. It's allowed for really detailed scenarios to be constructed about lahars given certain conditions. So thus far, we've discussed the concept of this unconditional hazard map that was pioneered by Crandall and Molyneux. It combines all the volcanic processes, all potentially impacted places, and it's aimed at long-range land use planning. And these are what we call the official hazard maps of the USGS, like capital H hazard maps. But early on, it was recognized that to supplement the unconditional maps, we would also need things like conditional hazard maps, which really focus on either one process, maybe a subset of impacted places, or examine a scenario. And these are more useful for short-term planning or coordination. This is what we saw start to be pioneered in that 1960 map of the Soufriere de Guadeloupe volcano. And so Lahars is a tool for constructing these conditional maps. This is an example of an application of Lahars to construct a conditional map of lahar hazards that my colleagues and I worked on at the request of the community of Trout Lake that sits at the foot of Mount Adams. And so we can keep track of where we are. We can see Rainier and we can see St. Helens, and this one right here is Mount Adams. All right, so back to the map. So you might recognize something different about this map than some other maps we've seen. On the map on the left uses a standard map view where every point in the map is viewed from directly above. Whereas on the right, we use a perspective view to try to improve the reader's ability to understand the relationship between the hazards and where people live. Recent research on volcano hazard maps has shown that this use of these perspective views are actually really advantageous for helping the audiences to interpret terrain and select better evacuation routes. So as I mentioned earlier, evacuation is really a critical life-saving action for mitigating the threat of lahars, and that's definitely the case here. So one thing I want to point out on this map is there's a disclaimer that says this is not a hazard map, and that's sort of a curious distinction, and it's because this is a map of possible volcano hazards. But the reason for this distinction is something I just mentioned a little earlier, that we reserve the term hazard map for the unconditional hazard maps that show all hazards. And we do this to avoid this confusion about which one is the hazard map for a volcano. Alone, a conditional map would really underrepresent the breadth of potential volcanic hazards at a volcano. So it's really important to draw that distinction and really to ensure that planners know which is the source for the best and most complete suite of information about volcano hazards and for the long-term land use planning. All right, let's take a step forward into the future of hazard maps. Future of hazard maps, bigger, better, faster. So to help me envision what would be possible in the future, I actually interviewed 3 colleagues and asked them the question, what is the future of hazard maps? So I want to say thanks again to John Ewart and also thank Dave Ramsey and Heather Wright for contributing some of their ideas. So 2 themes emerged from these conversations. The first was that new technology will enable us to do what we're already doing now, but better and faster. And the second is that evolving our communication strategies is really about evolving our communication strategies to better reach people who are at risk of volcano hazards. So first, I want to talk about the technology piece and how that could enable us to do the things we're already doing, but better and faster. And to begin, I want to share a little story about the 2018 eruption of Kilauea volcano in Hawaii. So Kilauea volcano in Hawaii is one of the most active volcanoes in the world, and so much so that it is considered the highest threat volcano in the US. Prior to 2018, the volcano had actually been erupting almost continuously for 35 years. However, on May 5th, 2018, the volcano entered a new phase of eruptive activity. Over the next 3 months, 14 square miles of the island will be covered in new lava, over 700 tons. So thus far in our discussion, we've talked about unconditional maps, we talked about conditional maps, but I want to introduce another type of map, and that's the situational or event-driven map. This is the kind we use in eruption responses. So in late May of 2018, I was asked to go join the eruption response and to help make maps to answer probably one of the most important questions on the island during this eruption, and that is, where is the lava? So this is an example of a map we produced on June 2nd of 2018 that was intended for the public. And so during the eruption response, we were making 2 to 3 new maps each day to provide situational awareness for decision makers and for the media and for the public, just to keep everybody abreast of the situation. Really, the biggest challenge we faced in making maps is that it's actually a pretty labor-intensive process to track lava flows and to transform that data into maps and then get them into the hands of decision makers. And so if you're wondering, well, how exactly do you track lava flows? Well, then stick around for the next slide, because I'm about to show you. So for making these maps, there are really 3 key data sources. And the first was satellites. Satellites are fantastic. You get huge aerial coverage from satellites, but they only crossed this area of Hawaii twice per day. So you only get 2 snapshots per day. And also there's a lag time between when the satellite actually collects the data and when you can actually put it into a mapping software. The next thing we're doing is helicopter overflights, including capturing thermal imagery in the helicopter overflights, which is also awesome again. But post-processing takes time to bring it into the mapping software. You also can't fly everywhere you'd like to fly in a helicopter, and it can take a really long time to cover large areas. Also, when we were in the helicopters, we were taking cell phone photos, which were cool, but we could text those back immediately when we landed to our colleagues who were making maps. But it still took time to compare the photos we had just taken to previous photos and then sketch in the lines to draw these maps. Another source of data was UASs, or unmanned aerial systems, aka drones, which are also great, but they do have a limited range, and the images they capture also require post-processing to be added into mapping software. So I think maybe you're getting the idea that time is a big factor here. So in the future, for better or for worse, I think eventually we'll have full Earth coverage of Wi-Fi, and that could actually enable some pretty amazing things in regard to responding to eruptions. Especially the real-time transmission of data from the field back into people who are making maps, for instance. This could reduce post-processing time. Or enable, especially if it was uploaded immediately to the cloud, maybe be processed on the fly. Also, you could possibly even start to enable real-time mapping using fancy feature extraction algorithms, which would be pretty fantastic. So like global Wi-Fi, in the future, we'll also have more satellites and larger constellations of satellites that could enable some really amazing capabilities. So this image we're seeing here is the eastern part of Kilauea volcano, and the image is called a differential interferogram. So what you need to know about it is it's a comparison of 2 measurements of the Earth's surface. They're taken by a satellite-based radar from about 2 weeks apart. So in the center, you can probably notice this rainbow bullseye pattern, and what that shows is the uplift that is caused by magma having moved into the area under beneath the surface, causing the surface to lift up. And this is happening prior to the eruption of Kilauea. So imagine a constellation of satellites with these radar instruments in them, positioned over this area, taking near constant measurements. In certain situations, in certain volcanoes, we might almost be able to map magma movement underground at volcanoes in near real time, which would be unbelievable. This idea could also be extended to satellites that are capturing and acquiring color imagery or thermal imagery, and we might be able to really speed up making maps of processes that are actually happening on the ground at that moment. And also just combine that with global Wi-Fi. We could maybe potentially even pipe maps directly into mobile devices as they were being captured by satellites. That would be a huge boon for supporting things like eruption responses. So earlier I said that we were making 2 to 3 maps per day, and in conversations with my colleagues, I learned that what we were doing in 2018 probably would have been totally impossible, maybe even just a decade before that. So many things that were really labor intensive during eruption response at Mount St. Helens in 1980, well, today nearly all of that stuff is automated. So I think that we can expect that before we know it, that same transition will occur, and the things that take us a long time right now will all be automated, and so everything will just be much, much faster. All right, moving on here. Like I said, we returned to talking about DEMs, and earlier we saw this image that was created using a technique called LiDAR. It uses an airborne laser scanner to capture very high resolution image of the surface of the Earth. So with LiDAR DEMs, you can use mapping software to reveal all kinds of features that are otherwise invisible. To illustrate the point, I want to show you a non-volcano example from our friends at the Washington Geological Survey. One of those powerful aspects of LiDAR is that we can use the processing software to basically remove the vegetation and see what the bare Earth surface would look like with the vegetation removed. So in an aerial view here, all we can see is the trees, but with LiDAR removing the trees, we can see that this river valley actually has a history of landslides along the river valley's margins. The USGS geologists are already using LiDAR at Crater Lake to reveal landforms related to the caldera forming eruption that actually formed Crater Lake. These are totally previously unknown. What's actually really fascinating about this is people that were really talented geologists who had been working in this area for decades before the advent of LiDAR were unable to see these features because of the forest. Looking forward to 2023, the USGS is actually planning to have the entire continental United States scanned by LiDAR by then. So who knows what we'll find next. And so the final thing I want to talk about is communication, and return to this simplified hazard map that was made in partnership with Mount Rainier in 2014. So this map uses volcano hazard zones from the unconditional hazard map, but the visualization was developed using a communication technique borrowed from public health called a single overriding communication objective. And the concept is really, what is the one key message about volcano hazards that you want visitors to take away from the park? And that message is that pyroclastic flows and lava flows occur in areas immediately adjacent to the volcano, while Lahars follow river valleys and are far traveled from the volcano. And this is just really some fundamental information about volcano hazards. This representation has actually proved to be really popular, and partially because I think it's really intuitive, and since then we've replicated it for all volcanoes in the Cascades. And so building on the success of these maps, working on new ways to reach our audiences in the future. Another frontier for us right now is the application of user-centered design to map making. So user-centered design is an iterative design process in which designers focus on the users and their needs in each phase of the design process. And it starts with this discovery phase, where we gather an understanding of who our users are, and then this ideation phase, where we identify user requirements. We can prototype solutions, and finally we can verify the designs meet the needs of our users. And so this is a practice that's used extensively in many industries, and basically to develop every cool app on your phone. But it's really new to the development of volcano hazard maps. And we said at the top of in the introduction, I'm currently leading a project to evaluate the map that we just saw, as well as we're looking forward towards applying this process to development of future products. Okay, so the last thing I want to talk about is this idea of being more inclusive with volcano science. And this is a poster that my colleagues and I just finished that focuses on the relationship between the lands of tribal nations and volcano hazards in the Cascades. And so one of the really interesting areas forward is how we can grow the way that we talk about volcanoes and volcanic processes by recognizing forms of traditional knowledge, including oral traditions. People have been living alongside these volcanoes since time immemorial, and to be an organization that is really a resource for all communities to be more resilient to volcano hazards, it will require us to acknowledge the value of traditional forms of knowledge and unparalleled scientific research. And so I think the incorporation of new voices into the world of volcano hazard work is actually very exciting. So throughout most of human existence, people haven't really known anything about how volcanoes work. And unfortunately, because of this, many people have died tragically in volcanic disasters. However, these disasters have motivated the science of volcanology forward, and with the evolution of technology and the ability to visualize volcano hazards and forecast eruptions, it's made it really safer for us to coexist with volcanoes. You know, volcanoes are fantastic and amazing places, and they still have many secrets yet to be uncovered. So with that, I'll say thank you so much for listening. I hope that you did enjoy the talk, and I hope you learned a little something about volcano hazards from the past, present, and future. And if you want to learn more, please visit the USGS Volcanoes website. And yeah, thanks again. I really appreciate you being here.